You might see a problem expressed like this with words. I have two connected boxes of antipasti, that's like my pickles and artichokes here, on a frictionless surface. It's horizontal. They're connected by a light string, meaning the string itself doesn't have mass that we care about, as in this figure above, where mass 1 is 10 kilograms and mass 2 is 40 kilograms. Force of 80 newtons is applied to the 40 kilogram box as shown. Determine the acceleration of each and the tension in the string. So that's the phrasing. What do we do with this? Let's look at the procedure. The first thing is we want to list our knowns and unknowns. So when you read through a problem, often you want to look until you see a number and then make a little list for yourself of the things we know. So I know mass 1, 10 kilograms. Very useful to include the units. Mass 2, what is it here? 40 kilograms. The applied force is 80 newtons, I know that. And what do I want to know? Determine the acceleration. And I've already said these two are going to have the same acceleration because the string can't stretch. And then what is the tension? Where is that tension? It's here between the boxes. So let's see how to set that up. The first step was list our knowns and unknowns. We have two more steps. I'll get the words out of here now that we have the data. We want to draw force diagrams so we can understand the forces on each object. And we want to use those free body diagrams, those force diagrams, to write and solve equations to tell us what we want to know. Always best to start with pictures and move on to equations after. What forces act on these pickles? Well, I know they have mass, and they're on Earth, I'm assuming. So they'll have a force that's their mass times g, the acceleration due to gravity, which we're going to say, for our purposes, is 10 meters per second squared down. You might know that's 9.8, but we'll call it 10. So 10 kilograms times 10 meters per second squared, it's 100 newtons pulling down, but it's sitting on a table, so is it falling? No. So something must be counteracting that 100 newtons. There's a normal force. The normal force here must be 100 newtons. And is anything else acting on this? Well, there's one other thing touching it directly, so that is the tension. So, have I missed anything? No, there's no friction, so those are the three forces on my green box of pickles. Let's label what this thing is. It's the weight, the force of gravity. I'll write it as F sub g. Now, to our red box, the artichokes, I know that same tension is pulling to the left on the artichokes. We also have the weight, the Earth pulling on this box. How hard does it pull? Well, it's the mass of 40 times 10, so 400 newtons. There's a lot of artichoke. Going up, we have a normal force on this box as well. How big is it? We know it's 400 newtons because it's supported by a table. And pulling to the right, we have 80 newtons of applied force. Now, why do we do this? Some of it is bookkeeping to make sure that we've accounted for everything in the system as far as forces on objects, but some of it is that I can read the free body diagram in each coordinate direction and find out what all the forces is. Let's look at the vertical direction first on the pickles. Pointed up, I have 100 newtons, down 100 newtons, so I have 100 minus 100 is the net force, that's 0. So I don't care that much about that right now. It's not very interesting. But in this direction, I do have a net force. The net force is T. So for the pickles, I have that the net force is T, and I'm applying a principle here. The principle is Newton's second law, which is that the net force is equal to the product of two things, the mass and the acceleration. So for the pickles, the net force is T, and the mass is, what's my mass of pickles? It's 10 kilograms equals 10 times the unknown acceleration. I now move on to the artichokes. What are the net forces there? Well, in the vertical direction again, 400 minus 400 is 0, but I have 80 minus t. 80 minus t. And that equals ma for this object. That's 40a. Now there are a number of ways I could solve this. I have two equations here. and 2 unknowns. I always want to check that. Does my number of equations, 1, 2, match my number of unknowns, a and t? It does, so that's good news. A technique I really like is to add these two equations together, because I see there's a t and there's a minus t, and if I have two statements that are true, two equations like this, and I add them together, that's also a true statement. So I'm always allowed to add two equations to make a new equation that's also valid. So here we'll have 80 plus t minus t is just 80, and that will equal 50 times a. How did I get that? 10a plus 40a is 50a, and then t plus 80 minus t is just 80. So 80 newtons equals 50a, so 8/5 is a, which we saw before. That's 1.6 newtons. Sorry, 1.6 meters per second squared, because it's an acceleration. Now how do I get the tension? Well, I take this a and put it back into either of my equations. I'll put it in here, so the tension is 10 times the acceleration. What's 10 times 1.6? The tension is 10 times 1.6, which is 16 newtons. So we see what the force is, the tension, and what the acceleration is. 1.6 meters per second squared.